All right, good afternoon, everyone. Today we are going to cover using differential equations to derive the beam equation. So things that we would see in the back of your text and references. Basically, they are equations to determine the angle of rotation about a certain point, as well as the deflection at a certain point, given a certain loading case. But what we're going to do is we're going to kind of go backwards. We're going to use our loading case, and we're going to kind of derive those. Well, not kind of derive those equations. We're going to derive those equations. So basically, what we want to do is we want to kind of look at what we're trying to figure out here. So we're going to consider this beam. So basically, we've got a simply supported beam with a uniformly distributed load across it. If we use our sign convention, like we've been talking about right here, where our moments shear forces and normal forces are positive given any sort of spot on the any sort of differential spot on the beam, then what we can do is if we take a very small section. So we've got that long beam that's simply supported, and we go anywhere on that beam and we take a little tiny section. So we mark off a spot called X, and then we take a little tiny section out of that, and what we're going to call that spot. So at any point X and any point Y, we're going to talk about that spot X, and then to the right of that delta X. So it's a really, really tiny spot. And actually, it's not at any spot. We have to assume that the bending occurs above the neutral axis. But what we're going to get is that we're going to get that we've got a load at that spot, just Q times X, because it's constant across the whole thing. On the left-hand side at point X, we have a shear and we have a moment. On the right-hand side, we're going to have a shear plus a tiny little bit of shear, right? Because the shear varies with the length. In this case, we know that it varies linearly if it's a uniformly distributed a load across the beam. And then we're going to have a moment plus a tiny little piece of moment. So we're going to take a section across the neutral axis of that element, and we're going to put a point in the middle of that element called A. So basically what we're going to come up with, if we use our equations of equilibrium, if we do the sum of the forces in the y direction, what we get is that we have, just moving from, I kind of go top to bottom here, top and then left to right. Q at X here is basically just our resolved load, right? So if we have a little element here, our Q at X times delta X, and it's Q at X, and then the length of that is delta X, our resolved load is just equal to Q at X times delta X, right? So no different than doing Q times L when we're still looking at the whole beam. So that's that term. We have our V from our left-hand side. Sorry, our V plus delta V from our right-hand side here. So that's this term here. And then our minus our V. So in this case, I said that the sum of the forces in the y direction, this is positive. I said down is positive in this case for whatever reason. If I simplify that, what I'm going to end up with is a change in the shear over a change in the X is equal to our uniformly distributed load, the negative of our uniformly distributed load. And all I've done is just rearrange this equation. If I continue to make that delta X smaller and smaller and smaller, so I approach 0, and then what happens is I can rewrite them as an integral, right? So if I make that delta X very small, and then I want to talk about it in tiny, insignificant, or not insignificant, but tiny changes, then I write them as dv by dx. Well, in this case, we get that the shear, the first derivative of the shear, is equal to our uniformly distributed load. So that's part one. Similarly, if I take the moment about that point A, and I say that's positive, so I go back up here, and I'm going to take the moment about this, what I'm going to get is that I'm going to draw that element over here again real quick so I can show what I'm doing. V, M, delta V, or V plus delta V, and then M plus delta M, and that's delta X, And then we had our Q at X right there. So what I did is I basically am going to say that if my moments are positive going this way, then that V times its moment arm, which is delta X over 2, right? So V times delta X over 2, it's going positive, is this term. Then I have V plus delta V, which is also rotating it positively, right? It's rotating it that way, times delta X over 2 here. So that's this term, plus M minus M plus delta M, right? So plus this direction minus that direction equals 0. I'm just applying equations of equilibrium. The Q term does not take into effect because when I resolve the load for Q, it goes through the origin. It goes through that point A, right? So Qx times delta X goes through that point A, so it doesn't actually contribute a moment. If you kind of break it down into two spots and resolve it on either side and try, they would just be equal and opposite, so they cancel each other out. Simplifying that, what we get is V times X over 2 plus V times X over 2, which simplifies to X, V times delta X. I got an extra term in there accidentally. Oh, delta V, yeah, delta V times delta X over 2. I'll get to that in a second, and then minus delta M, right? So M minus M goes to 0, and then I'm left with delta M. Delta V times delta X over 2 is much, much, much smaller than than V times X over 2. So what I'm going to basically say is that this goes to 0, right? So if I'm talking about an infinitesimally small unit, like micrometers, then that delta X is already very small, right? But that delta V is also going to be tiny. So those delta V and times delta X is going to be even smaller, right? So if something's really small, you multiply it by something that's really small, it gets orders of magnitude smaller. So we're going to basically say that goes to 0. So doing that, we can simplify the formula into this. And what it's going to come out with, and again, if I make that X, delta X, go really small or towards 0, then I can write it in terms of a derivative or an integral. And in this case, I get that the shear is the first derivative of the moment. So now I've derived that the shear is the first derivative of the moment, and that the load is the first derivative of the shear. So if I write that in integrals, the nice part is these come out to be separable equations. So if I write them out as separable equations, I can integrate both sides and come up with a solution. So rearranging the first solution here and then integrating on both sides, I get that the moment is the first integral of the shear. So it's basically saying the opposite, like that if it's the first derivative, then it's also the first integral. Just showing that they're kind of opposites. What we can do, and what we're going to show mathematically in a bit, is we're going to show that if we have our beam, I'm going to draw it again here real quick, because I like drawing beams. We have our beam here, and I say that this direction is X, uniformly distributed load. Q, I'll call it Q at X. Then when I solve over a distance of L, and I solve for my reactions, I'm going to get that this is QL over 2, and this is QL over 2, right? Just from using the equations of equilibrium. Then what I can do is I'm just going to show you kind of the answer before we start deriving the answer. If I keep this axis as Y, let's draw that down there, and I draw my deformation, it's going to look something like that. So this axis is Y, this is the x-axis, and that's the kind of the deformation diagram. So this at L over 2, this would be Y max, et cetera, et cetera. And this is the kind of thing you'll see in the beam tables. What I can also do, and I'm going to draw the next one, is that there's going to be an angle of twist. Or not an angle of twist, it's a rotation from a point to a different point. And what's going to happen is it's going to look something like this. And we're going to talk about that. We talk about it in 303, and we're going to talk about it in 305 again. next semester. But right now, I just want to introduce the idea that there's a rotation at a certain point about any other given point. And what it is it's actually the slope of the deformation here. So if I said the angle of twist at A with respect to B is going to be equal to the slope of the deformation, then as we go, there will be a zero slope here, right? So zero slope in the middle, and then it changes direction, kind of B with respect to A. Again, we're going to get into this later, but just trust me for now that that actually works. So that means if it's a slope, then it's the change in Y over the change in X. Then we can go further and say that our moment diagram is going to look something like this, which we know it will from doing statics. And we'll have an M max, and then we're going to have that M is actually equal to the stiffness times the change, the second derivative of Y over with respect to X. So if we go further again, so these are something I haven't proven yet, but they exist and they're true. But what I've also proven though is if I draw my shear force diagram, so I'm kind of going backwards what we do in statics, right? This is going to be equal to QL over 2. This is going to be equal to QL over 2, and that'll be negative. I've already just shown you above that my shear at X, at any given point X, is equal to the first derivative of the moment. And if I've said that the first derivative of the moment is equal to the stiffness times the second derivative of Y, then I can rewrite that as the stiffness times the third derivative of Y. And finally, because what I showed you up top there above this, what I also get is that if I have Q at X, in this case, Q at X over my L, I had said that negative Q at X is equal to the first derivative of my shear over my X direction, or with respect to X. Then I can rewrite it again as negative Q is equal to the stiffness times the fourth derivative of Y dx. And that's going to be an important equation that we're going to see quite a bit. So negative Q is equal to Y to the fourth, or to the fourth derivative. It's like writing Y IV is equal to Y 1, 2, 3, 4, Y quadruple prime. But that's going to be an important distinction that we're going to see again here. So these ones at the beginning, we kind of just have to trust me that they do exist, and we're going to see them as we progress in third year, and we're going to see them again later on. But they kind of exist. But I showed you kind of the proof of how this comes to be when I showed you that element above, and we're going to kind of expand on that as we continue on throughout these. And why is it useful? Why will we need to know all this? Well, because normally we can design for a load, and then we can develop our shear and bending. But then we also have to design, at some point, we have to take into consideration our deformation, or our displacement at any given point. Our loading conditions may not be super simple, but so we need a tool that we can use to come up with the deformation, because we need to take into account that as well. Not only will it hold up structurally, but our deformations within the limits of what we need to do for design. So that's what we're going to do. We're going to come up with I'm going to derive this whole thing. So, get my notes. If we take this term here, we're going to use this to come up with an answer, or what we're going to do for the how we're going to derive these things and prove that it actually works. So if we take a simply supported beam with a point load at midspan, then we draw the shear force diagrams and bending moment diagrams to look something like this. So the shear force diagram is going to be equal to P over 2, and then negative P over 2, and minus. Don't have to label that again, but I'm going to. And then our bending moment diagram is just going to look something like this. And that would be PL over 4, I believe. Anyway, I'm going to erase that. I'm not going to, it doesn't matter. But that's our bending moment diagram. So we've got two triangles, essentially, is what we're dealing with. When we're looking at the shear force and bending moment diagram, that original equation said that we can state the moment as a, the moment is the rate of change of the deformation, the second rate of change of the deformation. Trying to say that, figure out how to say this properly. If we use that, we can show that the moment looks something like this. Or sorry, our angle twist and our y is going to look something like this. So if I take the rate of change of our bending moment diagram, right, and this is exactly the kind of thing that we've done with what are we talking about? Oh, when we're dealing with the uniformly distributed load, the shear is a triangle. So when we do the graphical method of coming up with the bending moment diagram, we just take the area underneath it, right? So if the moment is the second derivative of y, then conversely, it means that the area underneath the bending moment diagram will give us the our rate of change for our angle of rotation, and then our deformation. So instead of taking the slope, now I'm taking the area, right? So if I take the area under there, then our angle of twist is going to look something like that, where it's positive and then it's decreasing, and then our deformation is going to look something like this. And it doesn't matter which side I put it on, positive or negative, but I just have to know which way it's going. That I'm basically just saying that if you can take the derivative, you can take the slope, you can reverse it and take the area, but then it gets multiplied by some constants, and we'll see that later on. But in order to go through this and actually prove this, we have to make a few assumptions. So these are kind of typical assumptions that we see in civil engineering quite a bit. We see that plane sections remain plane. Bending is about the neutral axis, so that all that means is that when we are looking at the cross section, the bending is 0 at the neutral axis, like we've seen before, for the stress. We have very small deformations, which we always assume in civil engineering, and that strain varies linearly within the distance to the neutral axis, and that's just because basically that means that E is equal to stress over strain. Stress over strain, and that's basically relates to our linear. It means we're in our linear elastic region. So if we exaggerate, actually just 1 second here. If we exaggerate our beam and we draw the deformation of our beam to look something like this, what we're going to get, let me see if I can draw this properly here. I'm going to really exaggerate it here. And it's going to look something like that. What happens when we bend it, if we're dealing with pure bending, and that's typically what we want to deal with, I have a neutral axis here, is that at some point, if we exaggerate that bending, these are going to go to a point, right? Any given point, if we take them a line from anywhere and bending, it's going to go to a point. I'm going to call that O. It's not exactly there, but for the purposes of this, it's going to be fine. I'm going to draw a line that goes straight through the middle of the beam to the maximum point. I'm also going to draw a line from that O, that origin of curvature, to our neutral axis, and I'm going to label that rho, and rho is actually called curvature. So sorry, the O is the origin of rotation, and rho is curvature. And you'll hear that, I think, in fourth year. You may hear it more in third year. And I'm going to draw another line kind of just to show curvature here. So I'm going to say that this is A prime, this point. This is D prime. This is B prime. And this is C prime. And then this angle here, because it's exaggerated, it looks really big, but we're going to call it delta theta. So there's going to be some change in angle that I'm going to be talking about. And that change in angle, if we draw it from the neutral axis into our Cartesian coordinates, is going to give me some version of delta x, right? So we're in positive bending, so we've got compression on the top, tension at the bottom. We've got a delta x that relates to an angle of rotation from the origin as well as the curvature. If I expand that element here, that AD element, I'm going to try to draw it like this. And I make it relatively large. So A prime, D prime, B prime, C prime, and I'm going to do my neutral axis up here. This distance at the neutral axis we're going to call delta S. So it's the actual increase in the size of the neutral axis. Actually, it won't be an increase because if it's about the neutral axis and we have zero bending, it won't increase. But it's going to be the measurement of the neutral axis over the at that kind of over that delta theta and the delta x. I'm going to define my coordinate system as negative y is down. And I'm going to just take another slice anywhere along the beam here. And that's going to be this point here from the neutral axis to here. It's going to be equal to delta x still, right? Because we already defined that before. And if I use similar triangles, etc., and the definition of how things like a circle and the radius, etc., I'm going to get that that's delta theta as well. And I'm going to label these points D and C. And I'm going to call this change delta U. So this is the neutral axis here. So I've got a delta S, which is the length of the neutral axis. And I've got, in tension, I've got a delta U, which is any given point at negative y. The change from our original length to its new length. All right, so I kind of am expanding this a little bit. What I'm going to get, if I go to trig and use some geometry, is that I get that my delta theta here is going to be equal to my delta S over my curvature. So basically that's saying that this here, it might be easier to see here, kind of the way that we define the pi, as long as it's really, really small, that delta theta is the same as saying this delta S here over the curvature is going to be equal to that angle in radians. I can also say that delta theta here, due to similar triangles, is going to be equal to delta U over delta S, right? So I'm coming down here, or negative y, sorry, that distance from the neutral axis. So the same as where it's the distance from the distance from the origin and curvature times the length is equal to the length of the at the neutral axis over the curvature, which is the distance from the origin of rotation to the neutral axis. So length of neutral axis over the curvature, which is equal to the distance from the origin to the neutral axis, can be the same as that delta U, which is the change in length, over the distance from the neutral axis. Sorry, at distance from the neutral axis over the distance to the neutral axis. I don't need to prove, I'm not going to prove it, but I'm going to just ask you to trust me on that. What we can also say then is we can equate them, and we can rearrange the equation in small increments the same way when we made x go to 0. We can rearrange them to say that 1 over rho is equal to our delta theta over our delta x. If that's okay, so that's kind of the end of the geometry part. Going back to strength of materials, we know that that strain is defined as the change in length over the original length. So in this case, when we go back to our diagram at the top there, and you can go back on your own time, the change in length, so our delta u of the rotation, so we had our delta s, and then we measured someplace down below, and this would be delta s, and then we had a little rotation or a little bit of a change, so delta u. So the change in the length of that fiber at that distance y, negative y from the neutral axis, we can define it as delta u over delta s. So we sub that back into this equation up here, equation 3, and we get delta s over delta rho is equal to delta u over negative y. Or sorry, we can sub it back into, that equation. We rearrange it so we get negative y over delta rho is equal to delta u over delta s, and then we can sub in strain. So then we can say 1 over rho is equal to E over negative y. And that's what we come up with here. So if we assume that we're in the linear elastic range, then we can use this property later on. So I'm just going to put a pin in that right there for now, and carry on with the derivation. So if we also look at a beam of any given cross section, it doesn't matter what that cross section looks like. We know from strength of materials that the stress varies linearly with the distance from the neutral axis, where you have maximum stresses at a given distance at the extreme top and bottom fibers, either in tension or compression based on how we're loading. If we take that property here and we look at it, so this would be our stress profile. So what it's saying is because the distance y to the bottom here is greater than the distance, let's call that yb and yt, yb is greater than yt, then we have a maximum stress at the bottom in this case. And we can actually say what the stress is at the top by just relating our y distance at the top, so over the ratio of our distance to the bottom fiber. And all that is it's basically just using the properties of similar triangles. I'm also going to consider two small areas, so delta A on either side, so either in compression or tension based on what our loading conditions are. In this case, the compression is at the top based on where the arrows are going, and tension at the bottom. So we're going to consider two small sections of area, one in compression, one in tension, and each at a different distance from the neutral axis. If we do our equation of equilibrium about the z-axis, then what we're going to get is that I'm going to have my moment, my applied moment about z. So it would look something, it's kind of hard to draw on this one over here, plus the integral of the area, so our small little tiny sections of the area, right? So the integral of the area with respect to the area of all those little sections, times their distance from the neutral axis times the stress at whatever point they're at. And that's from an actual definition. That's from one of the definitions that we've gone through when we did I kind of glossed over the derivations in 231, but this is something that we know. And this is basically a fancy way of saying that if we use my over I is equal to stress, all we're doing is rearranging that equation to say that m is equal to the It's actually stress over that times I. But the reason why I'm not putting it over, anyway, I sort of went off on a little bit of a tangent there. It's basically a derivation of that formula. So what we're going to end up with is a 1 over y kind of scenario. If we were just using the formula, because we're going to deal with top and bottom here. But trust me, this is how we get there. So that's how we get to the equation for the moment with respect to stress. I also said it varies linearly with the distance to the neutral axis. So I already talked about what that is, and basically using similar triangles, we can say that at any point x, the stress at any point x is equal to the maximum stress over the ratio of the distance from the neutral axis to the maximum distance from the neutral axis. So if we actually do that and we stop and say, instead of just any cross-sectional area, so any sort of nebulous form, we're actually just going to use a rectangular cross-section to prove this. So if we use that rectangular cross-section, I'm going to take that those two relationships, so the y and x is equal to the y over c, times the maximum. I'm going to sub that into the integral, and what I'm going to get is that I'm going to get that it's going to equal that, and that all equals 0. Yeah, so that ought to equal 0. I didn't write that. Right, so now I've got it as a function of our stress, which is going to be a constant. This is a constant because the cross-sectional area doesn't change. So now all we have is a variance of our y squared as a function of our area. So this is the equation that I end up with. I rearranged it and just isolated in the moment. If we go back again to 231, where I was saying don't worry about the derivations for the moment of inertia or the first moment of area. Really, you don't have to worry about it again, but this is one of the definitions that I told you not to worry about. All we're going to do is use that, and we're going to sub it into this equation here. So when we sub it into this equation, now we've got the integral of y squared dA. I'm going to get that m is equal to negative xi over c, which is really a rearrangement of that formula that we know here. So that's where it ends up, where we get the 1 over y value. So that's where we're at the point where we've kind of derived the equation and shown why the equation m equals y over I works for the stress at any given point on the cross-sectional area. I'm going to introduce another property called the section modulus. It's constant for any given cross-section because it's just the value of I, which is constant for any given cross-section, right? So we have I of the I-beam over the C value, which in this case we've defined as the maximum distance from the neutral axis to the extreme top or bottom fiber. So that's going to be constant for any given cross-section. And I'm going to introduce that. So we're going to put that in, and we're going to say that for a rectangular cross-section, S is just equal to L cubed. But if we just go back to our derivation, we get our stress at X, that we've seen before, is equal to my over I. We have a linear elasticity, so we can use that the modulus of elasticity is equal to the maximum stress over the maximum, or over the strain, or the stress at X over the strain at X. And we can sub that in again and say that strain is equal to my over EI. Going all the way back to equation 6, so all we're doing is using a bunch of properties that we already know because of the assumptions we made or because of strength of materials, and we're just using those equations to kind of rearrange our idea of how moment relates to stress and etc. So if we go back to equation 6, which is this, the 1 over rho is equal to the strain times 1 over negative y, and we sub in the idea that our relationship with the modulus of elasticity, and we sub that in, we can get that our strain is equal to the negative moment times y over EI, which is stiffness. So that's something that's, again, is constant for a given material property and cross-sectional area. And then we're going to sub it in here, and we actually get that the curvature is equal to m over the moment over the stiffness. So this means that when the moment's increased, the inverse proportion of the curvature is also increased. So what it means is that as we increase the moment, so think about a beam that looks like this. So as we increase the moment, what we're going to get is something that looks like small moments. We're going to have a very small radius, or not radius, but a very small curve. And then as we increase it, we get bigger and bigger. If we look at where the origin is, if the origin up here, it's way up here, right? The origin is going to get longer with smaller moments. As we increase it, the origin is actually going to get smaller. So the inverse is going to increase. The inverse of the proportion of the curvature is actually going to increase. So that's all that's saying. And conversely, if we increase the stiffness of the beam, so we make it harder to bend it, then the curvature decreases. So we end up with something like this, right? Because if it's harder to bend, the more moment we apply, the less deformation we're going to get. Therefore, the curvature is going to increase overall. I hope that makes sense. And that's kind of just to say that stiffness, increasing the stiffness resists moment, and it has an effect on the curvature. If we go through geometry, we can show that all of that equals this. I don't expect you to derive that, but just understand that we can say that all of that equals this. Because we assume small deformations, then dy by dx is small, and therefore the dy by dx, so if you took a square of a small number, you get a very, very, very small number. So that's going to be equal to 0, essentially. Just checking my notes here. And then we can basically state that the second derivative, or the curvature, is related to the second derivative of the dy by dx. Which means that we can say that the 1 over the curvature is pretty much the y double prime, so the second derivative of y with respect to x. And we sub that back into equation 16, this one up here, where 1 over rho is basically equal to y double prime. Then we get that fundamental equation that we talked about at the beginning. So all that we did here was just go through a really long proof of that the moment is the second derivative of the deformation times the stiffness. Then basically, because we showed right at the beginning that that negative q was equal to dv by dx, and that m was equal to dv by dx, or dm, sorry, did that backwards. And we showed that v was equal to dm by dx. We sub those back in using this principle here, and I can actually state that my shear is equal to the third derivative of my y, right? And then because I said that dv by, or v is equal to dm by dx, so if I take my dm by dx, I get y triple prime, so, or equals ei times y triple prime. And then if I take the derivative of the shear again, I get the negative q is the same as ey to the fourth derivative of the deformation y as a function of x. So these are kind of important things that we want to know in order to be solving for how to derive our beams. What I'm going to do is I'm going to break the video here. I'm going to take a pause, and I'll separate the video into 2 sections, and then I'll upload the next video with boundary conditions, and we're going to go through an example of how this actually works. All I've done to this point is actually go through the proof of that this all works out. That basically, instead of just trusting me this time, I actually went through the whole derivation and said, this is why this works. Now what we're going to do after in the next video is we're going to use them. So I've proven that they worked. Now we're going to use them, use the fact that they work in order to solve for our beam equations. So I'll take a pause here, and I will see you in the next video.